Hello, welcome back. This is Calculus by Dr. Oz. Today we are going to try to approximate integrals by using the power of the power series. So this is another application of power series. So we have two integrals, one for cosine x squared. In fact, these are definite integrals. So one for cosine x squared, another one for arctan x squared. And when we have the approximation for each case, we do not want to have an error more than 10 to the minus 4. So now the question is like, how many terms would you keep in the power series of, let's say, cosine x squared or arctan x squared, so that when you integrate this function by using their power series, you wouldn't make an error more than 10 to the minus 4. Okay, so to get started, in fact, please refer back to the table of power series of elementary functions, because we need the power series of cosine x and arctan x to reproduce the power series of cosine x squared and arctan x squared. I don't want to give you more heads up because I will talk more about that in the video, but we are going to have in total of 2 videos and covering each case. Okay, so let's get started. Right, in this example, we're going to make use of the known power series to approximate the value of the integral. So we're going to use the power of the power series towards approximating integrals. All right, so in part A, we have cosine x squared. So cosine x squared has the same power series representation as cosine x, except you replace x by x squared. Okay. So what we can do, we can go back to our power series table for elementary functions and grab the power series representation for cosine x to start with. And here we go. We have cosine x represented by its power series, and the interval of convergence is for all x minus infinity to infinity. So and let's just copy that down back to our problem. All right, there we go. Okay, remember that we need cosine x squared. So what I'm going to do here is just I'm going to replace x by x squared here. So it's going to be x to the 4n divided by 2n factorial. Okay. Once I have this representation, since, by the way, the integration is on 0, 1, and the interval of convergency is for all x, so we're safe in terms of the analysis here, okay? So why don't we go ahead and put that power series down in the integrand. Okay, so we're going to do like term by term integration. Okay, that's going to take us to the infinite series. Infinite series. I forgot the n here, so let's just put that n back at the step before, minus 1 to the n, right? X to the 4n plus 1 divided by 2n factorial and 4n plus 1. Okay, and this should be evaluated at lower and upper limits, so 0 and 1. Okay, and when you plug in 1, well, this is 1 to the power of 4n plus 1, right? That's going to take you to 1. So then you're left with minus 1 to the n, 2n factorial, 4n plus 1. Okay? And that's us plugging in the upper limit. And if you plug in the lower limit, it's going to be all 0 because all of the terms in the infinite series, if you expand them out, have x in it. So when you plug in 0 for x, those terms are gone. So 0, in fact, doesn't contribute anything towards the integration here. So then we are left with an infinite series, and remember that we want to have an error less than 10 to the minus 4. Okay, and we're going to be careful on that because we have now an infinite series, which is an alternating series, right? And I want to approximate the values of that with the error less than 10 to the minus 4. So at this moment, I totally suggest you to go back and check the description of the alternating series remainder theorem. So we have, let me just explain that in a few words here. All right, here is me reminding you the alternating series remainder theorem. So if you have an alternating series minus 1 to the power of n plus 1, so this is an infinite sum, and let's say like the sum converges and converges to s, and you want to make an estimation. Let's say like you keep the first capital N terms in the sum, and this one Rn representing the tail of the sum, so that's an infinite sum itself. So Sn has only finitely many terms, n of them, capital N of them. So then the actual value of the sum minus the approximation, which is the absolute value of S minus Sn, is in fact Rn, right? Absolute value of Rn. And the alternating series remainder theorem says that the upper bound for Rn is just the very immediate next term where you cut off the series, because I cut off the series at the end term, right? So it's a1 minus a1 plus a2 minus a3 all the way to minus 1 to the power of n plus 1 a capital N. And the very next term comes with an plus 1. So the theorem says like the error, upper bound of the error cannot be greater than an plus 1. So we're going to use this idea in terms of finding Sn. So the question is like, how many terms should we keep in the sum? So in other words, what should capital N be so that the Rn, the absolute value of Rn, would be less than upper bound of the absolute value of Rn would be less than 10 to the minus 4. Okay, so this is a trial error part from your end. So you can list down A1, A2, I don't know, A3, A4, A5 maybe, and whichever one gives you a value less than 10 to the minus 4, then let's say like A4 gives you something less than 10 to the minus 4, then the summation of first 3 would be like a very good approximation for you. And that approximation would have the error less than 10 to the minus 4. Okay, so with a few trial error, you can pause the video and then do your own trial error from your end. And what is an, by the way? An is in fact this term, so it's 1 over, so if there's a hypothetical 1 here, right at the top, so 1 over the bottom. All right, 1 over the bottom is your an. Okay, so go ahead and then use your calculator to check A1, A2, A3, and A4. And turns out that 1 over 4 times 4 plus 1, okay, times 2 times 4 factorial. Check this out. This is less than 10 to the minus 4, and that corresponds to n equals 4. Okay, that corresponds to n equals 4. That's good news. This is A4. Okay. So that means I can keep only the first, well, I can keep like S3 for the approximation. So in other words, I can look at the sum starting from 0 all the way to 3 to represent the approximation of the infinite series. Let me just write it in the new slide. Okay, here we go. So what I just said is that this integral is approximated by only the summation up to n equals 3. And if you use your calculator and if you just list all the terms like a0, a1, oh, I forgot the minus 1 to the n, sorry. There's also minus 1 to the n at the top, I'm sorry. Okay, so we still have the alternation obviously, and that is approximately equal to, if you use your calculator, 0.90452. Okay, this is a very strong result because going back to the original problem here, cosine x squared is not something that you can use the integration techniques that we learned in the previous sections because of the x squared term here. That makes it double complicated, and that's why we are trying to use the power of power series to approximate those definite integrals. Okay. All right, so that takes care of part A, and I'm going to finish this video right now, but you should move on to part B in the next video. All right, see you.